we are going to find the potential inside and outside a charged sphere. So we have this sphere, and we want to find what is the potential if the point that we want to find the potential is outside the sphere, and how about when it's inside the sphere. We found out in some other problem, or you can look in the textbook and see that the electrical field outside the sphere just looks like a point charge. So this is a vector expression. You have the Coulomb constant, the total charge, and then divided by the distance to the origin squared. And then times a direction vector that just points radially out of your sphere. So outside the sphere looks like a point charge. Inside the sphere, wee bit more difficult. You still have your Coulomb constant, so far so good. You have the total charge, yeah, okay. But then you have the radius cubed, and you have to multiply with the distance to the origin. Wee bit different than a point charge. When you find your potential, you have to integrate from a reference point, and usually it's easiest to pick either infinity or 0 because they are easy to put into your integral. Here we use infinity and it works. If you find, or if you run into a problem where you try using infinity as your reference point, but you cannot solve the integral, try picking another reference point like a or 0 or some other constant. We need to take our electrical field and then the dot product of the electrical field and some direction. And here we pick the direction vector to be just the r vector. Then this vector problem E dot dl or dot, if we pick the direction to be the radius vector, then these two are parallel and it simplifies to a scalar problem instead, or to a scalar integral. So we need to take minus the integral from infinity or reference point to the point r, and then we need to take the electrical field, or the magnitude of the electrical field, Coulomb's constant, and the charge 1 over r squared, and integrate with respect to r. We then get the minus sign stays, the constants change nothing, and then you find the antiderivative, or the integral of 1 over r squared, which is minus 1 over r, evaluated at infinity and at r. And if we evaluate it just at the point r, these cancel, then you get a constant, Coulomb's constant over r, and then minus, if you evaluate it at infinity, you get some constant times 1 over infinity, which is 0. So this is just our answer. The potential outside the sphere is given by this expression. And if you apply the Nabla operator, or if you find the gradient of this potential, you will find the electrical field with a flipped sign. So that works. The potential inside the sphere is a wee bit trickier, because you have to say, okay, so we need to take minus and then integrate from infinity to our reference point, and then E dot dl. But outside the sphere you have one electrical field, you have this expression, and inside the sphere you have another electrical field, so you need to work your way in from infinity. So we need to split this integral into two components, or two parts. First you go all the way from infinity to the outer shell, so you go all the way from far away, all the way, work your way in to the shell, to this surface. And then out there you have E out dr, but then you have to make your way from this shell, from the radius, into your point where you want to find the potential. So minus the integral from the radius to some point, then you have E in dr. So the potential inside depends on the electrical outside and inside. So the potential inside cares about what's going on outside. If we look at the first expression here, we need to take an integral of E outside from infinity to some other point. We did all that already just with evaluated at infinity and small r. Now we evaluate it at infinity and capital R, so we just get an expression that looks like this one, only we switched a small to a capital R. So the first part, this first part simplifies to Coulomb's constant, the charge, and then the radius. This other part here, we have to integrate E inside, and E inside is this expression. So the Coulomb constant, the charge, radius cubed, those are all constants, and then you have to integrate R with respect to R. So we get, these are constants, they don't change. And then the antiderivative of R with respect to R is 1/2 R squared evaluated at these points. We still have all those constants in front of it. And we could rearrange something. I'll just simplify it a bit further. This 2 I'll move down here, and here I'll multiply and divide by 2. It doesn't change anything. So we're left with 2 Coulomb's constant and the charge with 2r minus constants, and then this evaluated at these points gives us r squared minus capital R squared. And this expression can be simplified because if we take this r cubed and we distribute r squared out here, then this simplifies to 1. Now these two fractions look like each other. So we get 2 times some constants minus, and then you have the same constants, and then you have that, and then this simplified to a 1. And now we can see that we have 2 of these, and if we distribute this, then we get another, and then we get the constants times some relationship between the distance and the radius. So if we have enough room, then this whole business simplifies to Coulomb's constant, the charge over 2r times 3, and then the distance squared over the radius squared. So we see that the potential outside is pretty straightforward. Just take your Coulomb's constant, the charge, and then divide it by the distance. The potential inside is a wee bit trickier, and you have this factor 3 that came from simplifying this expression. So you see that the potential inside, it cares about what's going on outside, but also if you look at the final expression, it really cares about what the radius of this sphere was. But that's what we wanted to find, the potential outside the sphere and inside the sphere. So we are done.